If you want to train machine learning models faster and more efficiently, you need to know about JAX, which is quickly becoming one of the most important tools in the field. It combines NumPy-like syntax with just-in-time compilation and automatic differentiation, making it perfect for high-performance deep learning. Also, JAX is specifically designed for seamless execution on GPUs and TPUs. In this video, we'll cover the basics of JAX. We're going to go through a simple example of building and training a neural network in it, and we're also going to learn how to utilize the TPU for maximum speed. So let us get right into it. Alright, so we're going to take a look at JAX in this video today, and I want to structure this video in 3 segments. The first one is going to be an introduction to JAX. I want to show you what JAX is capable of, what we can do in JAX, what JAX is all about. Then I want to move on to an example where we build a neural network using JAX. We're going to train it on the iris dataset, so a basic classification task. And finally, I want to show you how we can use TPUs in JAX. We're going to use Google Colab for that, so that we can accelerate the learning even more by using TPUs, which is not as straightforward and simple in PyTorch, for example. So let us get started right away. The first thing that we need to do is we need to get JAX on our system. And this is quite simple, but you also need to consider what kind of backend you want to use. So basically, to just install JAX, you just have to say pip or pip3 install JAX in your command line. But of course, you can specify different backends. If you just do install JAX, you're going to install it for the CPU. But if you want to use acceleration devices, for example, a GPU or a TPU, you need to install the proper backend. So you need to say, in this case, pip3 install CUDA12 or some other version, or TPU, for example. So depending on what kind of device you have on your system, you need to install JAX, and then in square brackets, you need to specify what kind of device you plan on using. And of course, you can have multiple versions. I think in my case here, if I run pip freeze and then grab JAX, you're going to see I have JAX CUDA12, so I have both. And if you're not sure what kind of CUDA version your GPU supports, if you have an NVIDIA GPU, you can just run NVIDIA-SMI, and you're going to see up here the CUDA version, in my case 12, so I can use CUDA12 with JAX here. One thing that I want to mention here right away is that I'm going to refer a couple of times to the documentation of JAX, just because this video today is not going to be a full crash course. It's not going to be a full tutorial on JAX. It's more like an introduction into JAX. We're going to cover some technical details. We're going to build actually a working example of a neural network in JAX, but still we're not going to cover all the aspects of JAX. We're not going to cover all the important aspects of JAX. And because of that, I'm going to refer you a couple of times to the documentation. If this video performs well, however, if you guys are interested in JAX, I will consider making a more detailed course when it comes to JAX. But this today should already be quite interesting for a lot of you guys, because we're going to cover many features and many aspects of JAX. But just as or for the sake of completeness here, you can go to the documentation, to the quick start section to see what JAX is all about. And here in the sidebar, you can see all the concepts, or a lot of the concepts that we're going to talk about today, explained in more detail, like just-in-time compilation, vectorization, differentiation, and so on, which we're going to talk about here in a second. So we're going to start here by opening up a Python file. I'm going to call this basics.py. And here I want to just cover a bunch of things about JAX. First of all, let's look at the name. What is JAX? What does the J stand for? What does the A stand for? And what does the X stand for? So J stands for just-in-time compilation, or JIT compilation. JIT, or just in time. And this basically means that we compile sections of code in advance, or the first time we use them, and then we just run the bytecode instead of always using the interpreter. So we have a section of code, some function, for example, where some stuff is happening here. And if we compile that function just in time, so if we use JIT compilation, this function will just execute faster because it's compiled already. We have the bytecode that is being run on GPUs, TPUs. We have it ready. We don't have to do it every time from scratch. This is the, in a nutshell, benefit of JIT compilation. Then we also have A, which stands for automatic differentiation. So this basically means that JAX allows us to easily and automatically differentiate functions, to take the derivative of functions. If I have a function in Python, if I define a function square, for example, with an input x, and this function returns x to the power of 2, JAX makes it very easy for me to just take that function and get the derivative of that function, in this case 2x. Now this is quite a simple function, but JAX does that with all sorts of activation functions, with all sorts of loss functions, we can just go ahead, say, give me the derivative, and it's going to give us the derivative. This is automatic differentiation, and probably one of the USPs here when it comes to JAX, X, which stands for XLA, Accelerated Linear Algebra, is basically what allows us to run this on TPUs. This is basically an open source machine learning compiler. And yeah, this combination here makes JAX very powerful. It's a little bit like a combination of NumPy and PyTorch with TPU support, I would say. And what I want to do now is I want to briefly provide some structure for this basics file here. So what are we going to cover in this basics file before we move on to the example? We're going to start by covering JAX as NumPy. This is what I would like to call this section, because JAX basically has its own version of NumPy, JAX NumPy, which for the most part is quite similar, but there are some differences. We're going to talk about that in a second here. Then we're going to also cover JIT compilation, as already mentioned. We're going to cover automatic differentiation, we're going to cover automatic vectorization, and we're going to cover in the end also randomness, because randomness is handled in a more, let's say, special way in JAX compared to NumPy, for example. And let's get started now with JAX's NumPy. So JAX, as I mentioned, has its own version of NumPy. Now we can import JAX, but we can also import JAX.NumPy. Usually this is given the alias JNP. And this is now what we're going to use instead of NumPy when it comes to working with arrays when we work with JAX. So for the most part, as I said, it's going to be the same. So I can say A is equal to JNP array, the same way I would say NP array. I can say 1, 2, 3. I can also say B is equal to another array. And then I can do basic stuff like A plus B. I can do stuff like JNP dot square root, for example, of A. I can do stuff like JNP dot mean of A. And I can also do stuff like A dot reshape, -1, 1. So that is basically like NumPy. I can run this and you're going to see this is exactly what we would expect to happen if we were to use NumPy. Quite simple. We just can work with JAX NumPy instead of NumPy. However, they are not exactly the same, not in all situations. For example, one thing that I cannot do with JAX is, or with JAX NumPy is, I cannot just assign values to certain positions like this. So I cannot say A1 is equal to 10. This doesn't work in JAX NumPy because it says type error, JAX arrays are immutable and do not support in-place item assignment. This is something I can do with NumPy. If I say import NumPy as NP, and if I copy this down here and I remove the J, that is going to work. This is a possibility in NumPy, not a possibility in JAX NumPy, because their arrays are immutable. Now, there is actually a section in the documentation called JAX the sharp bits. And basically this is a section or an entry, you could say, where the differences are highlighted and also some pitfalls. So for the most part, as I mentioned, you can use JAX NumPy like you would use NumPy, but there are some things to consider. Since this is not a full course, I'm not going to cover all of this stuff here, but you can look at that if you're interested to know what you can mess up and what works differently here compared to NumPy. Quite interesting. I would recommend that. So let's move on now to the JIT compilation. So the JIT compilation, as I mentioned, is compiling things just in time, compiling things when they're used. So let's say I have some function, my function, and this function takes some input x and returns some result based on calculations. So I can say, for example, this returns JNP where, so I have some condition, if x is divisible by 2, I'm going to say return x divided by 2. Otherwise, what I want to do is I want to say 3 times x plus 1. So maybe you know this as the Collatz algorithm or the rule of the Collatz algorithm. Basically, we just divide a number by 2 if it's divisible by 2. Otherwise, we take 3 times that number plus 1. And there's also a conjecture that this always terminates and so on, or always ends up in the same place. But let's say this is my function now. Now, we can also import time to measure the difference in execution time depending on what we do with that function now. So let me just get rid of all that stuff here. And let's go and see how long it takes to compute the result given an array. Let's say the array is JNP a range 10, so 10 values. And then what I want to do is I want to say start is equal to time perf counter, end is equal to time perf counter. And here now I'm going to do my function array. Now, one thing that's important here is to understand that JAX has asynchronous dispatch, which means that when we do something with JAX and the result is an array, this array is not going to be evaluated immediately. So when I run this, even if this takes an hour to actually get the result, we're going to immediately jump to end. So I will do start, then the function call, and then end immediately, and we're going to see an execution time of less than a second probably, even though the result is not calculated yet. The reason for that is this asynchronous dispatch. JAX basically returns control to the Python program as quickly as possible, and the result is not evaluated until it's necessary. If I want to force the evaluation, if I want to wait for the evaluation to finish, I need to call block until ready was the function name. So this basically forces us to wait for this to become evaluated, to be evaluated. And then we're going to move on with the measurement. We're going to say end, print end minus start. And when I run this now, you're going to see this takes 0.2 seconds now. Let's run this again. 0.19 seconds. Let's run this again. Yeah, that seems to be the average time it takes. And I can actually decrease that time by just adding JIT compilation. So by just saying on top of that function, jax.jit, and this just-in-time compiles that function, which means that the first time this function is executed, it's going to be compiled to bytecode and ran afterwards. So when I do it just like that, you're going to see we get 0.05 seconds, which is already a speed up, but I can get a massive speed up if I call that function multiple times. So if I go ahead, for example, and say that I want to warm up the function, so I want to compile it already, if I want to say empty result or empty variable, my function array, this is the warm up, so to say, this one is going to be very, very quick because we already have this function compiled the first time we call it. And when I run this now, you're going to see we get 0.00019 seconds. So much faster than before, this time even faster than that. So you can see this E minus 0.5 here, which means 5 decimal places shifted to the left. Yeah, so that's the basic idea of just-in-time compilation. We can take a function, we can just annotate it with jax.jit, and it's going to be compiled when needed. This is especially useful for training steps, training loops, because these are things that are executed multiple times. Now, one thing that I want to show you here to understand in more detail what is happening behind the scenes is we can take a look at the bytecode that is produced by the just-in-time compilation. And we can do that by using the function jax.makeJaxper. Now, Jaxper is its own intermediate representation, its own language basically for JAX. What happens is every time we compile a function, we basically reduce it to a sequence of primitive operations, and we can take a look at that by using makeJaxper. So this is just now for the sake of seeing what this looks like. This is the code that is then actually sent to the device, to the GPU, CPU, TPU, whatever. And how we do that is we say jax makeJaxper my function. We pass the function as an entity. As a result of this function call, we then get a callable. Here we pass the parameter as before. So we don't do my function array. We do makeJaxper my function and then call this result with array as a parameter. And when we print that, we're going to see the resulting Jaxper code. So I can run this. And we're going to see this is actually what happens when we compile in JAX. Now, you don't need to understand this, but if you want to look into that, there's also, again, a section in the documentation. This is the intermediary or intermediate representation that JAX uses, and it's also free of any side effects. This is something that I would cover maybe in more detail if I make a tutorial or a course on JAX. Now, one more important thing before we move on to the differentiation is there are certain things that cannot be JIT compiled. You cannot just use jax.jit on any function. If you have, for example, let's call the function f of x. If you have a function where the parameter is used as a condition for the flow, so if you do something like if x modulo 2 equals 0. So you don't do it with J and P where, you do it like if x then something, then return 1, otherwise return 0. If you try to JIT compile that, this is not going to work. So jax.jit on that, if I call f of 10 here, this is not going to work. It's going to give us a tracer bool conversion error, attempted Boolean conversion of traced array with shape bool. So this is not possible, but again, I refer to the documentation for more detail. All right, now let us move on to automatic differentiation, a very important feature, a very central feature of JAX. And the basic idea, as I already mentioned in the beginning, is you can take the derivative of functions easily and automatically. So let's say I have a function square of x, and I return x to the power of 2. Now, let's do the derivative manually. So f of x is x to the power of 2. F prime of x is 2x. F double prime of x is equal to 2. And then f triple prime of x is equal to 0. So if x, for example, was, let's say x is 10, then here I would get 100, here I would get 20, here I would get 2, and here I would get 0. Let's see if we can do that easily with JAX. So what we do here is, let's first start by printing square of 10. Or actually, let's go and say value equals 10. And actually what we need to do here for the differentiation to work is we need to work with floats. So you don't want to say 10, you want to say 10.0 to make it a float. And then we're going to just say square value. That, of course, is going to give me, first of all, we need to get rid of all that. That, of course, is going to give me now 100. And what I can do now is I can call jax.grad for gradient, jax.grad. And I call this on the square function. So again, we do the same thing as with make jaxper. We say jax.grad, pass the function. This is going to differentiate it to take the derivative. And then we apply that result. We call that result and we pass value. So when I run this, we're going to get 20 as a result. And what I can do now is I can say jax.grad applied onto that as well. So just do jax.grad on jax.grad of square, and that is going to give us 2. And I can do it one more time. Jax.grad on that. This is going to give us 0. Now we can of course continue to do that, but it's not going to change much because the derivative of 0 is always going to be 0. So we're going to get the same result over and over again. But what we can also do is we can also take partial derivatives. So let's say I have some function, let's call it f, and f takes x, y, and z. And what we do here is we return x to the power of 2 plus 2 times y to the power of 2 plus 3 times z to the power of 2, for example. And now let's say that x, y, and z are in my case all equal to 2. Let's compute the partial derivatives manually. So the function is x squared plus 2y squared plus 3z squared. The derivatives are quite simple. If I have df dx, it's just going to be 2x. Everything else is a constant, so we can ignore it. And basically, if I do the same thing for y and for z, I'm going to get 4x and I'm going to get 6x. So in the case of the values being all equal to 2, I would get 4, I would get 8, and I would get 12. So let's see if that's the case. Let's see how we can do that with JAX. I can just go ahead and say print f of 2, or x, y, z actually, like this. This is going to give me expected to callable value got 2.0. Okay, the problem is just the code up here. I think I made a typo when I edited something. Let's run this again. We're going to see I get 24. Why? Because I have 4 here. I have 8 here, so that's 12. And I have 12 here again, so I have 24 as a result. Now, let's see what happens when I say jax.grad of f, and then we call that again. Now, the important thing is we need to specify here now a parameter argnums. And if I say argnums equals 0, it's going to take the first parameter and it's going to take the partial derivative with respect to the first variable. So in this case, x. And when I do that for 1 and for 2, I'm going to get the partial derivative for y and the partial derivative for z. So when I run this, we get 4, 8, 12 as expected. So you can do it like this as well. There's also another way to do that. If we have, for example, let's define the function f again. If I have this, or actually let's do it up here. If I have this as a list, so if I don't say x, y, and z, if I say array, and I replace x by array 0, and I replace y by array 1, and I replace z by array 2, then basically I'm passing a vector here. What I can do is I can call, of course, the whole thing on a list of x, y, and z. Now I don't need to specify argnums anymore. I can just say take the derivative of f and pass the list. And what I'm going to get is I'm going to get also a vector of derivatives. So I'm going to get 4, 8, and 12 in an array here. All right, now let us move on to automatic vectorization. This is interesting because vectorization basically means I have a function that works for a single value and I want to be able to apply it onto batches. How do I do that? Now, the example I'm going to use here is quite trivial and quite simple. But this is also something that happens with more complicated functions. And then, of course, you don't want to do it manually. So you don't want to take a function that works for a single value and manually make it compatible in the most optimal way with batches, with matrices, basically. So you can do that with JAX automatically. For this, what we're going to do is we're going to define a random key. Now, we're not going to talk about randomness yet. We're going to talk about this in a second. But for now, just generate a random key by saying jax.random.key and pass a seed, for example, 42. Doesn't really matter what we're doing here right now. Just accept that this is necessary for randomness. So we're going to have this random key here. And then we're going to randomly generate a weight matrix. So we're going to say capital W is going to be equal to JAX random normal. And we're going to say that we want to pass the key here as a randomness basis, let's say. And we're going to have the shape 150 and 100 here. So you can think of this to be a scenario where we have inputs that have 100 values per input. So we have 100 values per input sample, and we have 150 neurons in next layer. So that would be the weight matrix to take these 100 inputs and 150 weights per input, basically, and to do the calculation for the hidden layer, essentially. And then we have our X matrix as well, so random normal. We're going to now just reuse the key, even though we shouldn't do that, just for the sake of simplicity here. And we're going to say that we want to have 10 different input samples with 100 values each. So let's say this is now the scenario I have, and I have a simple function which is calculate output, and this function takes some input X, and all it does is it returns the dot product using JNP, so JNP dot of the weight matrix and this individual input sample. So that would be one of the 10 samples here. That is my function. Now, in order to make it compatible with the full batch, in order to be able to use that function on the entirety of X, on the entirety of capital X, I either have to change it myself or I have to somehow do it in a more intelligent way. So one very naive approach would be to go ahead and say batched calculation loop, let's call it like this. And what we're going to do here is we're going to get the full matrix X, and we're going to just stack the individual results. So we're going to do jnp.stack, but what we're going to actually do is we're going to just call the function individually on every single input. So calculate output of X for X in X. That's it. That's a very naive and inefficient solution. Now I can also use linear algebra here, in this case quite simple, to derive the fact that I can just do this as a simple dot product of the matrices. So I can say, let's call this manual x. What we're going to do here is we're going to just return JNP dot and then x and the transpose of the weight matrix. That is also possible. First of all, that's still not the most efficient way. Second of all, it's oftentimes not that easy to do it if the function here is more complicated. So what we can do actually with JAX is we can use a function called vmap to do this automatically in the most efficient way. So we can say batched calculation vmap, for example. I'm going to define this now as a lambda expression because it's a one-liner. Lambda, so a function that takes capital X, the matrix, as input. We're going to just say that all we do here is we vmap, or actually, is this even necessary? Can I not just say... no, I think we have to do it like this. Lambda, capital X, and then we're going to say jax.vmap. We're going to pass our calculate output function, and this piece right here vectorizes that function. So by doing jax vmap, actually I think this, it should be equivalent. Not sure about this. Maybe I'm talking nonsense right now, but I think this should also work. We just do jax vmap, we vectorize that function, which means now instead of handling one sample, it handles a batch of samples, and this is done automatically for us. Whatever that function is, this is done automatically and now works for batches. So let's go ahead and say start is equal to time.perfCounter. End is equal to time.perfCounter. And then let's just do batch calculation loop of x. And then print end minus start. Copy this, paste this twice, add some spacing here, change this to be equal to manual, and this to be equal to vmap. So I can run this, and what you're going to see is that these two are not very efficient. This one is. Now we can also compare in terms of equality. So I can, do we have NumPy still imported? No. So let's go import NumPy as NP. And we're going to use the all close assertion. So I'm going to say np testing all assert all close. And we're going to assert that these two these three results are actually the same. For this, we're going to say, I want to know that the batch calculation loop for x is at least kind of similar to what I get from the manual. And I'm going to allow for an absolute tolerance here of 1e minus 4 and a relative tolerance 1e minus 4 as well. And then I'm going to do the same thing. I'm going to use not exactly transitivity here, but if this and this is basically the same, and then I say that manual and vmap is also basically the same, then I can assume that all three are basically the same. So let's run this, and if it doesn't crash, it means that we have basically equality. So yeah, this is what you want to do. If you have a function like this that does a simple calculation given a single sample, you can vectorize it easily, automatically, without thinking about it by just doing vmap. So just JAX vmap the function, and now it works on matrices. All right, now before we get to the example, the final thing I want to cover here is randomness. And I don't want to get into too much of the technical details here, but I want to explain the basic idea, again, taken from the documentation. There is a section on random numbers. Maybe I can pull it up here, which explains basically why things are the way they are in JAX. I want to give you a very high level, simple explanation of that. The basic idea is in NumPy for randomness, we have a implicit global state that has to be somehow coordinated and shared, and everything depends on that global state. So we have seeds, and that's basically it. Now with JAX, we have three requirements that we want to fulfill. We have the reproducibility, we have the parallelizability, and we have the vectorizability. If we use NumPy's way of doing things, we basically only get the first one, which is reproducibility. So we can get the same result given the same seed, but that's basically it. We cannot parallelize and we cannot vectorize efficiently. So what JAX does is, since it has to run on multiple devices, and since the JIT compiler reorders instructions, we have to use a different strategy to guarantee all the three requirements. So what JAX does is it uses keys, and these keys can be splitted and they can be distributed accordingly. And again, if you want to know all the technical details, theoretical details, either I'm going to do a more detailed explanation in a course, in a crash course on YouTube, or I'm going to refer you to the documentation where you can read about this. You will find the links in the description down below. But the basic idea is that in JAX, we work with keys and not with seeds, and these keys can be splitted into multiple keys, and all of this can be then parallelized easier. Let's put it that way. So if I want to do randomness, we saw it already up here. I have to use a key. The basic rule of thumb here is you don't want to ever reuse a key unless you explicitly want to get the same output. So if I say key is JAX random key, I can pass a seed. And once I consume that key, once I use that key for anything, I don't use it again. So not for the same use case, I don't use it for anything because there might be some correlation in the randomness. Once a key is used, we throw it away. We don't use it. It's dead to us. So if I have this key and I use this key to do a random normal distribution, so if I do JAX random normal, and I use that key as input, this key is consumed. I don't use it ever again. I have to use a different key. Now I can also use that key to create new keys. So I can say key dot, or actually I think it's JAX dot random split key, and the result of that is going to be two keys. Let's call them key 1, key 2. Now these two keys are unused and basically as useful and as powerful as the initial key. So these are just two keys now. However, we used this key to generate these two keys, which means this key was consumed. We don't use it anymore. Key is dead to us, so we don't use it for anything else anymore. If I want to do something else, I use key 1, key 2. And of course, I can distribute them across devices, which is kind of useful. But also, I can do it in a different way. So first of all, key 1 and key 2 can again be splitted. So I can say JAX random split key 1. And that is going to result in two new keys. But then, of course, key 1 is consumed. So I get key 3, key 4, and I can use them again. But I can also do it in a simpler way. I can just say keys and then JAX dot random split key and then a number of keys, 10 keys, for example. If I print that, we're going to see I have 10 different keys generated based on the first one. So that is one key, that is another key, and so on. So you don't need to understand all the details here. Again, if you're interested in the technical details, go to documentation to understand why it's done that way. What you need to understand in general is this is how randomness is handled in JAX. If you want to do something random, you need to provide a key as a basis for the randomness. So if you do a normal distribution, a sampling, whatever you do with JAX random, you will need to provide a key as a basis, and you always want to use a key only a single time. You don't want to reuse a key. That's the basic thing you need to understand here. Now let us move on to the second part of this video where we're going to go through an example. We're going to build and train a full neural network from scratch in JAX, which means we're going to define the weight initialization. We're going to define the forward pass, the training step, the loss function, everything from scratch. The only thing we're going to use JAX for is for the automatic differentiation. We're going to use the JIT compilation. We're going to use some of the activation functions, which are already part of the neural network module of JAX. So it's going to be quite low level. It's not as simple as just defining the layers and choosing an optimizer and then going for it. We need to do more stuff manually, but it's not as difficult as doing it from scratch in NumPy. So it's kind of in between. So let us get started by first installing an additional package if you don't have it on your system. Now we're not going to use it for machine learning. We're going to use it just to get the data set. We're going to work with the iris data set, a very basic classification task. And we're going to use it for basic pre-processing and train test splitting. So the package is scikit-learn. A lot of you guys already know it. It's a package for traditional machine learning, so for support vector machines, random forests, and so on. But we're going to use it primarily to get the iris dataset and to do some pre-processing. So let's open up a new file, example.py, and we're going to start with the imports. I'm going to import JAX I'm going to import jax.numpy as JNP. And we're going to also say from sklearn.datasets import load iris. From sklearn.model selection, we're going to import train test split. And from sklearn.preprocessing, we're going to import one hot encoder and standard scaler. All right, so let's get the data. We're going to say that the data is equal to load iris. Then the x data is data.data. The y data is going to be data.target, but we're going to also reshape it to get it into the proper shape, vertical shape for the neural network. And then we're going to apply one hot encoding to the output values because we want to have probabilities. We don't just want to have a class label. Right now, if we take a look at y, we're going to see, actually, we don't have sklearn data sets because I mistyped this. There you go. So we have the 2s and we have the 0s and we have the 1s. And what we actually want to have is we want to have this one hot encoding structure where we have for each class either a 0 or a 1. So every class becomes its own feature. It's going to be either yes or no. And we can do that easily by defining a one hot encoder. So encoder is equal to one hot encoder. We're going to pass y. We're going to say sparse output is equal to false because we want to have, as I said, the representation where we have the 0s and 1s. Actually, we don't pass y yet. We just say encoder is equal one hot encoder, sparse output false, and then we just say encoder fit transform y, and the output is fed into y. Now, if we take a look at that, we're going to see that we have the structure with 0s and 1. So you can see instead of a 2 or instead of a 1, we now have 0, 1, 0. Instead of a 0, we now have 1, 0, 0. And instead of a 2, we now have 0, 0, 1. All right. So what we also want to do is we want to split our data into a training set and a testing set so that we can train our model on one part of the data and evaluate it on another one. X-train, X-test, Y-train, Y-test is going to be the result of calling train test split on X and Y. And the test size is going to be 20%, so 0.2. 20% of the data is going to be testing data, 80% is going to be for training. And of course, we want to scale the training data, or we want to scale the X data in general, because we're working with neural networks, which are scale sensitive. So X-train is going to be equal to, first of all, I need to define a scalar. Scalar is equal to standard scalar. And then we do scalar fit transform X-train. And then we do X-test scalar transform X-test. The reason we do fit transform here is because, of course, we're training the scalar on the training data. We're not going to train it again on the testing data. We're using the scaling method that was chosen based on the training data. We're applying it onto the test data. We're not fit transforming again because then we would not be using the same scale. So this is how we do that. And then we're going to define our functions. The first function is going to be the init params function, the initializing parameters function. And the parameters for our model are going to be weights and biases. We're going to have a very simple neural network. To understand this, we're going to have a structure where we have the input. The input is going to go into hidden layer 1. Then that is going to go into hidden layer 2. And then we're going to get the output. So we're going to get input, weights and biases, or weights, hidden layer biases, weights, hidden layer biases, and then again weights, biases. So we're going to have 3 sets of weights, 3 sets of biases, and we're going to do that here. We're going to initialize all of that here in the init params method. So the first thing that we get is going to be the input dimension. The second thing is going to be the hidden dimension 1. So the number of neurons in the hidden layer 1, the number of neurons in the hidden layer 2, and then the output dimension. Now, input dimension and output dimension are going to be based on the data. So input dimension is whatever the shape of one instance is in the data set. And the output dimension is going to be whatever the shape is of one output sample. So in this case, the one hot encoded 011 or 001, for example. And finally, we also want to have a random key that we can split to use it for different purposes. So we're going to need 3 random keys because we're going to do 3 random initializations. How we're going to do that is the following. We're going to say random keys is equal to JAX random split, as we learned about this. Random key, we want to split this into 3 different keys. And then what we want to do is we want to say the first weight matrix is going to be JAX random normal distribution based on the first key, so random keys 0. That is going to be the basis for the randomness. We're going to define the shape input dimension, hidden dimension 1. Makes sense because we have the input dimension, and then we have like how many individual values does one input sample have. Then I have how many neurons do I have in my first hidden layer, and then I need to have interconnection, so I need to have a weight matrix to connect these two. So that is going to be the first layer. Then we're going to also have a bias. So we're going to have bias 1, and that is going to be not random. We're going to initialize the bias as 0. So we're going to say JNP dot zeros hidden dimension 1. So for this, we don't need randomness. If we were to also initialize this randomly, we would need 6 keys, but now we only need 3 because we're only going to use this for the weights. So now let's do the same thing for weights 2, bias 2, weights 3, bias 3, and here also random keys 1, random keys 2. And another important difference here, of course, is hidden dimension. Here we're going to say output dimension. And here now from input dimension to hidden dimension, from hidden dimension 1 to hidden dimension 2, and then from hidden dimension 2 to output dimension. So the basic idea is, maybe let me sketch that briefly. Basic idea is I have some input. Let's say I have 3 input values, or these are the, let's call them I1, I2. This is not the most beautiful drawing here, but I have these 3 input values. Then I have some neurons here. Let's say I have 4 neurons. That here would be my input dimension, 3. That would be my hidden dimension 1, 4. And now for each of these, I will need a weight. So I will need 4 weights for the input 1. I will need 4 weights for input 2. And I will need 4 weights for input 3. So I will need 12 weights total. This is what we're doing here. And then I have another layer. Let's say this one has 5 neurons. Then this would be hidden dimension 2. And then I would need 20 weights here. And for the bias, I only need as many weights as I have neurons. Hope this makes sense. So what we do is we return weight matrix 1, bias 1, weight matrix 2, bias 2, weight matrix 3, bias 3. And now we have the parameters initialized when we call that function. The second thing we're going to define is the forward pass. So what happens when I get some input forward given parameters and x. So we pass the parameters, the weights and biases to this function. And what we do is we just apply them. So we say, again, W1, B1, W2, B2, W3, B3 are the result of, or not the result of, we're going to get them as parameters here. So we're going to get whatever we have at this specific moment in the training loop. We're going to have to pass this to the forward pass. We're going to get the weights and biases, and then we're just going to apply them. To get the first intermediate result, we're going to take the inputs. We're going to do a dot product with the weight matrix 1. We're going to apply onto that, or we're going to add to that the bias, and then we're going to apply onto this result the activation function. So we're going to say JNP dot product, and we're going to have x and weight matrix. Then to that, we're going to add the bias 1, and all of this will be fed through a ReLU activation function. So JAX.NN, this is something we didn't talk about yet. So JAX has a neural network module. JAX.NN ReLU just implements a simple ReLU function. For those of you who don't know what ReLU is, quite simple. It's a very, very simple function. You just have a coordinate system like this, maybe a more beautiful one. Coordinate system like this. Okay, doesn't look very good, but everything that where the input x is below 0, we just get a 0 all the time. And then once we get to the positive values, we just get the identity function. So if I get 1 as input, I get 1 as output. If I get 2 as input, I get 2 as output. But if I get anything below 0, I will always get 0 as output. That is the ReLU function. It's good enough to break linearity, and it's quite simple, easy to take the derivative off, and pretty effective. So then for H2, for the second intermediate result, we do a dot product of H1 and weight matrix 2 and bias 2 here, again, ReLU function. And then what we do is we do a final dot product here, H2 and weight matrix 3 plus bias 3, but this time we don't do ReLU because these are now the logits which we're going to feed into the softmax activation function. So we're just going to return the logits here. All right, so maybe one more time here to give you a visual explanation of what's happening. We have the inputs, let's call them in. We have hidden layer 1, or let's say the hidden layer is just a bunch of neurons here. We connect all of them. We have the weights and biases here. And then what we get as a result of the ReLU function here, the output after this layer is called H1. We take this H1 and we connect it again, or we connect all these different neurons here. We connect them here to the next layer. This is really not a beautiful drawing. But that basically, after we do the weights, biases, ReLU, we get H2. Then we do another set of weights and biases, and then we have the logits, which are going to be fed into the softmax function to get probabilities. Softmax basically gives you, for each class, not just a value, but a probability. So all the values add up to 1. You have 100% probability in total. And yeah, this is just convenient to work with sometimes, depending on what you do. The next function is going to be our loss function, loss of n. And this is what we're going to take the derivative of. So we're going to use the gradient function of JAX, so JAX.grad, on this function. This is what we need to derive, this is what we need to differentiate, because of course we're interested in the gradient of that function to know which direction to go into to optimize. So loss function, take parameters x and y. The reason we also pass the output here is because we need to, of course, see what the loss is, and to calculate the loss, we need to know what the correct answer is. And also we're going to pass here L2 regularization parameter, which is just going to be by default 0.001. The idea here is to make this function more complicated. We're going to add regularization that penalizes large weights. So we want to keep the weights small. The larger the weights are, the more we're going to penalize the loss function. The more we're going to increase the loss because of the large parameter size. So the logits are going to be the result of calling forward on params and x. So we're getting x, we're calling, we're doing a forward pass, we're getting the logits, we're turning them into probabilities by using JAX NN softmax. Logits like this. Then we calculate an L2 loss, which is going to be whatever our parameter is for the regularization times. Now we're going to take to sum of the weights, or the squares of the weights. So we're going to say JNP dot sum weight to the power of 2 for weight in params. And now we only want to have every second parameter because we want to start with the first one, but then we want to jump over every other parameter because we're only interested in the weights, not the biases. So we're going to do : 2. Yeah. So basically we're taking every weight and we're squaring it. We're summing all of this up and we're multiplying this with some parameter for regularization. This leads to smaller weights. So yeah, that's the idea. And we're going to return here a basic cross entropy loss. So negative JNP mean of JNP sum y times JNP log probabilities plus, and then some very small number just to not have 0. So 1e minus 8, axis equals 1. And to that, we're going to now add our L2 regularization loss. That is our loss function, not as simple as the square function we looked at before anymore. So it is more complicated than that. And we have a bunch of parameters. And this is basically what JAX can do for us. Instead of taking the derivative manually, JAX can do it for us easily, which is what we're going to do now in the training step. So the train step function is going to do the actual movement. So we're going to, as a summarization, what we do is we initialize parameters, we feed data through the network, we get some result. In the beginning, it's going to be a random result. Then we're going to see how good is that result, how bad is that result, and where do I have to go to make it better. This is what the loss function does. And the training step then actually takes that step into that direction. So we get the gradients of the function by calling jax.grad onto the loss function. We pass parameters, we pass x and y. By the way, of course, all of this needs to be passed into training step as well. So we pass here parameters, we pass x, y, and also a learning rate, LR. So how much do we want to move into that direction? And then we return. For each parameter, we take a step into the direction, into the opposite direction. So think about it that way. When you have the gradient of a function, it shows you the direction of steepest descent. So what you want to do to decrease the loss, since we're not trying to maximize the loss, you want to go the opposite direction. So we take a parameter and we go, so minus, we go into the opposite direction of the gradient. How much depends on the learning rate. So learning rate times gradient. So the learning rate scales the gradient. The gradient tells us where we need to go to decrease the loss function with respect to this parameter. And we do that in a very small way. So for param and gradient in zip, params, gradients. That is our training step. And this is something that you want to put a jax.jit on top of, because this is going to be ran multiple times. So this makes sense. JAX, JIT, and then this runs faster. Now, let us also implement here for the evaluation an accuracy function. The accuracy function is going to take parameters x and y again as input. And we're going to get the predictions. We're going to say JNP argmax. So get the position where the value is the highest. And we're going to forward params x. We're going to just get the maximum logits. So the highest activation, so to say, is going to be our prediction. The targets are going to be what's actually true. So JNP argmax based on the actual data. So the actual true data, the ground truth. And we return JNP mean, where predictions are equal to targets. Meaning we're looking at all the samples. Where are these two equivalent? So where is the highest activation in my predictions equal to the highest activation in the true test data? How many times is that the case on average? This is my accuracy. Yeah. More functional way to express this maybe. And then finally, we want to also have a data loader. The data loader is just going to provide the individual instances as batches. So we get here as a result, or as input, we get the full X input, we get Y, we get batch size, and then we do for I in range from 0 up until the length of the input matrix. Batch size is going to be the step size. And what we do is we just yield the next batch, which is current position plus, or current position up until current position plus batch size. And the same thing also for Y. So I plus, or I up until I plus batch size. And that is going to give us the batches. So that's it for the functions. Now we're going to actually just run this. So we're going to define the parameters. We're going to say that the random key we want to use is equal to JAX random key. Come on, JAX random, or actually this was, no, JAX random key. We're going to pass, you can either pass a static seed like 42, or if you want to have a different seed every time, you can also use something like time. So you can actually import time. This would be a quick hack to get a different value every time. Int time. Just use that as input and you're going to get a different value every second, a different key every second. So input dimension is going to be determined by the data. It's going to be xtrain shape 1. Reason we go shape 1 is because shape 0 would be the amount of data, so the number of samples, and shape 1 is what's the shape, what's the length of an individual instance. Then for hidden dimension, we're going to go 16. For hidden dimension 2, we're going to go 8. And then we're going to say the output dimension, of course, depends on Y train, shape 1. The learning rate, let's set it to 0.005. And then the batch size, let's set it to 16. We don't have too much data. And then epochs, let's set them to 200. Maybe a bit too much, but let's just do it. Now we're going to initialize the parameters. We're going to say params are equal to init params. And we're going to say input dimension. We're going to say hidden dimension 2. We're going to say output dimension. And we're going to pass a random key. And now, finally, for epoch in range epochs, we just want to say for every batch, so X batch, Y batch in data loader, given X train, given Y train, and given a batch size of batch size, which is, as we said, 16. Now we're going to say params is equal to train step. Train step, params, X batch, Y batch, learning rate. So again, idea is you initialize the parameters, and with every epoch, with every batch, we update the parameters based on the gradients. I'm going to go through all the code again to explain it briefly, but repetition is always good. So I'm going to repeat myself a couple of times. So if epoch is divisible by 10, so every 10th epoch, we're going to print, we're going to say train accuracy is equal to accuracy, where we do params, X train, Y train, and then we're going to do the same thing for the testing data, even though usually you would want to probably use a validation set for that. Makes more sense. Test data is for final evaluation, not for evaluating every epoch usually. But we're going to do it just like this now. And we're going to say fstring epoch, and then train accuracy, and then test accuracy, Hope this works. And finally, we're going to then say final test accuracy is going to be accuracy called on parameters, X test, Y test. And maybe one more thing that I would like to do here is I would like to define that I don't want to have more than 4 decimal places. All right, so I'm sure I made some mistakes. So let's first try to run this before I say anything about that. There you go. We have a problem. Oh, there's a mistake. We have init params here as a first parameter. To init params, of course, this is supposed to be input dimension. So let's run this again. And now we hopefully see, there you go. We get 63% accuracy. Let's see if we can get a better accuracy if I run this again. Now we get 96% accuracy. It doesn't seem to change too much. So maybe one thing that we could try is we could try to increase the learning rate. Let's see if that helps. Or maybe it's just randomness. Sometimes it's going to be randomness. Okay, so you can run this a couple of times. I also got, I think, a couple of times 100%, which of course doesn't mean that it's the better model. It just means that in this particular situation, it got 100%. But you can see that we get a pretty decent accuracy. So the neural network seems to work. So let's go through this one more time just to explain this. We load the data, we reshape the output data just to make it vertical. We hot encode it to have 0s and 1s instead of the actual class labels. We do a train test split. We initialize parameters randomly. For this, we use random keys, as explained in the beginning. We have weight matrices. We have bias vectors, which are 0 by default. In the forward pass, we take these parameters. We just do dot product, add the bias, ReLU activation function, dot product, add the bias, ReLU activation function, dot product, add the bias. That's it. We get the logits. In the loss function, we turn them into probabilities using softmax. We also have a regularization for the weights. We want to keep the weights small, so we do that like this. Then in the train step, we do automatic differentiation of the loss function. We get the direction of steepest descent. We go into the opposite direction for each parameter, a small bit determined by the learning rate. And we have an accuracy function for evaluation, a data loader to handle batches, and that is how we do it in JAX. Now, last but not least, I would like to briefly show you that we can easily use TPUs with JAX without any configuration, without any code changes. It just uses a TPU if one is available. The only thing that we need to do is we need to install the proper backend if we don't have it, as mentioned in the beginning. So if you are on your own server and you have a TPU there, what you need to do is you need to install Python, and then you need to install using pip JAX, but with square brackets TPU, just to install the TPU backend. Besides that, everything is done for you. You don't need to do anything. You can use the TPU to accelerate your code easily. Now, what I have here is I have a Google Colab notebook opened up. So I have this environment type here, the runtime type, changed to TPU. So I'm not using CPU or GPU, I'm using TPU. And if I use something like Torch, you're going to see, if I say import Torch, and then if I say torch.cuda.isAvailable, you're going to see it says false. So I don't have a GPU, I don't have a CUDA device enabled. I also have some code here that I can copy paste to show you that the basic PyTorch functions don't find any device here. You can use PyTorch on a TPU, but you have to use an external package or a separate package for that, which is, I think, Torch XLA. But with JAX, it works out of the box. So what you can do with JAX is you can just say import JAX, and then you can say jax.devices, and it's going to list the available devices for acceleration. So in this case, it's going to list, hopefully, all the TPU cores. As you can see, we have TPU device ID 0, 1, 2, 3, and so on. These are TPUs that we can use for acceleration. Now, we can also see which device is being used when we perform a calculation. So let's import jax.numpy as JNP. And let's do a basic calculation. I say x is equal to JNP dot once, and I'm going to say 1,000, 1,000. And then I'm going to say y is equal to JNP dot, and I'm just going to do a dot product of x with itself. When this calculation is done, what I can do is I can say y.device to see where the result is located. And if I do that, you can see the result is on the TPU device. We can also see that this is actually happening by doing something that takes quite a bit of time. So I'm going to copy paste some code here again. This is a basic matrix multiplication. We have a random key here. We have JAX random normal. This is actually a ChatGPT example. This is why I copy pasted. We have A and B, which have 20,000 times 20,000 as a shape here. We do a matrix multiplication, just in time compiled. And when I run this, this happens very, very quickly on the TPU. It's done in 0.75 seconds. If I do this on a GPU, it takes longer. If I do this on a CPU, it's impossible. So we can actually try that. I can go to the GPU environment. There I don't have a TPU. So now I'm connected. I can run the code again. We can see now CUDA is available for PyTorch probably. There you go, true. Then we can go down here to import JAX devices, and we're going to see CUDA device ID equals 0. If I perform that calculation, the result is going to be on CUDA device ID 0. And now when I run this, it's going to take much longer. It already does the matrix multiplication, but it takes some time. It doesn't do it as quickly. So this is proof that you can use the TPU with JAX easily. So that's it for this little introduction into JAX. I hope you enjoyed it. I hope you learned something. If you want to see more JAX content, the most important thing to do is to like the video, to hit the subscribe button, to leave a comment in the comment section down below. The more successful this video is, the more likely I'm going to do more JAX content. If you like this type of video, let me know in the comment section down below. Let me know by hitting the like button. And in general, as always, subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and